Welcome back. We're now going to cover chapter 17, Doppler Effect theory, and the equation for the Doppler effect is f prime is equal to f v plus or minus v observer divided by v minus plus v source. The v here means the velocity of the sound in the medium. In this case it's air, but it could be any other medium. So we'll just leave it, instead of calling it v of sound, we'll just leave it as v and just know that that's the velocity of sound. So right now I want to explain to you the idea behind the Doppler effect, and then show you why the observer's velocity is in the numerator and then the source's velocity is in the denominator, and then what does it mean to say plus minus and what does it mean to say minus plus in the denominator, and then explain when to use which one. Okay, so the Doppler effect, basically we can summarize it as this: it's an apparent shift of the frequency of sound due to the motion of either the source or the observer. So right now let's focus on if the source is stationary. Imagine there's a stationary source, and it could be any source of sound producing device. It could be a fire truck, it could be a speaker, it could be anything that's just standing still. Okay, so imagine it's a fire truck like this, and it's producing sound waves like this, and it's producing sound waves of a certain wavelength, right? So the wavelength, the distance between peak to peak, is called the wavelength, right? So imagine now the source is stationary. Source is stationary, and then now imagine if the observer, it could be you driving in the car, right? Imagine if the observer is driving towards the source of sound. What's going to happen? Well, it's going to seem like the velocity of the sound wave, the velocity of the sound is this way, so let's just call it v. It's going to seem like the velocity of the sound waves is more than it is, because your velocity is coming towards this and then the sound is coming toward you. It's basically like two cars coming toward each other on the freeway. If you're driving 60 miles an hour this way and another car coming toward you at 70 miles an hour, it seems like that car is coming toward you a lot faster. So let me just draw that. If you're going 60 miles an hour this way and another car is coming toward you 70 miles an hour, it looks like that car is coming toward you at 130 miles an hour, right? So with respect to you, it looks like you're almost stationary and the car is headed toward you at 130 miles per hour. So the effective velocity of the sound wave is increased now. V prime is equal to v of the sound wave plus the v of the observer. Okay, now using the equation, velocity of sound is equal to the wavelength of sound times the frequency, right? So we can say now, because the velocity of the sound has been increased, v prime is the new effective velocity of sound with respect to you, right? So we can say here, v plus v observer is equal to wavelength times frequency, f prime. F prime is the new frequency that you will be hearing. Now what's going to happen to the wavelength? The wavelength of the sound wave is not changing because the source is not moving. As soon as you reach here, right, then you're driving toward it, then you're going to meet the other peak. So you're meeting the peaks of the waves a lot more often than you would have if you were just stationary. So only the frequency of the sound source increases. This increases because why? The effective velocity of the sound wave increases, but the wavelength of the sound wave remains the same. Okay? So then we're going to solve for f prime. Okay, so we're going to have here f prime is equal to, divide both sides by lambda. So we have here v over lambda plus v observer over lambda. Okay, we can just factor out the lambda, and we can say 1 over lambda v plus v observer. Then we can use the fact that the original velocity of the sound is lambda f. We say lambda is equal to v over f. So we have here f prime is equal to 1 over f, v plus v observer. And then this f goes to the top. You have f over v plus vo, which is effectively this equation, right? So what is this saying? The new frequency heard by you, f prime, is equal to the regular frequency that it's producing, which is f divided by the velocity of the sound. So in this case, the source is not moving. So when the source moves, this thing disappears. Okay, and if you're driving towards the source, you put a plus here. So its effective frequency increases. So when do you use this plus then? You use the plus when you are driving towards the source. So driving towards source. Of course, with the same argument, if you drive away from the source, then if its effective velocity seems like it's decreasing, and then the peaks meet you less often than they would have. So you use the minus driving away from source. Okay? So now let's talk about what happens when the source itself moves. In this case, what happens, the wave ripples that it creates in front of the source are shortened, and the wave ripples behind the source are lengthened, right? So it goes like this. And then these wave ripples behind it are actually lengthened. The ripples that it creates in front of it are shortened. Why? Well, because after creating a ripple of sound, the source is itself moving towards the creation of that sound, right? Wavelength shortened. We can say lambda prime is equal to the actual wavelength that it's creating minus the amount that it's shortened, delta L, and the delta lambda, the distance that the source moves. The distance that the source moves, distance is the velocity of the source times the period of the sound wave. Right? In other words, the distance that the source moves during one period is the time for it to create one wavelength of sound, right? The distance that the source moves is equal to velocity of the source times the period. So that's the delta lambda. Lambda minus velocity of source times the period of the sound wave. Right? The wavelength, so imagine if I draw one peak and now I draw another peak. This is lambda. The sound wave was originally here, and it moved a certain distance, right? Let's say here. And then it created the second sound wave, right? So therefore it created a sound wave here. So you see it's shortened to lambda prime. So this distance here is the delta lambda. So then what are we going to do? We're going to say lambda prime is equal to lambda minus V source, and then the period is equal to the 1 over the frequency of the wave, right? Because we can say velocity is equal to lambda f, and then the period is equal to 1 over frequency. Okay, so we have V is equal to lambda prime f prime. So our goal is to calculate what the f prime is going to be, right? V, and the V is equal to the velocity of the sound. So lambda prime is equal to lambda minus V source over f times f prime, right? And then we can take this f prime, then we can say V over lambda minus V source, okay, over f. And the next thing we can do is use the fact that velocity is equal to lambda f, therefore lambda is equal to velocity over f. So we can write here v over f minus v source over f prime, right? And then factor out the f, and then it goes to the numerator, right? So therefore what happens, f prime is equal to f v over, and then on the bottom you have v minus v of source. Okay, therefore this is exactly this equation. Okay, so if the observer is not moving, now the top portion, the numerator cancels out, right? There's no observer moving. V is just the velocity of the sound, which is this. And then on the bottom you have velocity of sound minus the velocity of the source. So interestingly, what happens here is we use the minus in the denominator when the source is driving towards the observer, right? So in the denominator, it tends to reduce the denominator, right? That means it tends to make the frequency higher. And then when you use the plus in the numerator, it tends to increase the number too. So then when do you use the plus? You use the plus when source is driving away from observer. For the same logic, then you use a plus on the bottom. When you use a plus on the bottom, it tends to do what? It tends to increase the denominator, which tends to decrease the effective frequency heard by the observer, okay? So next I will give you some examples of this and how to utilize it, okay? Thank you very much.